Hello and welcome to the next video in our kinematic series, where we're going to extend on the ideas of displacement time graphs and look at velocity time graphs. So similarly with a displacement time graph, a velocity time graph will hope to describe how an object's velocity is changing over time. So we'll have time on the x-axis, velocity on the vertical axis. Now, in the previous video, we looked at a displacement time graph where the gradient represents velocity. And in a velocity time graph, there are two other things we need to know as well. Displacement, if you've got a velocity time graph, displacement comes from finding the area under the graph. Now, why is this the case? Displacement and velocity, let's have a look. So velocity is displacement over time. Okay, displacement given by a symbol s, and for us to find displacement, you'd multiply v and t together. So when you multiply v and t together, that means you're multiplying these two variables, which means you multiply them and you want to find area. Okay, that's why the area under graph is displacement. And as mentioned before, for acceleration is the change of velocity over time. So that's why the gradient of a vt graph gives you acceleration. So there are obviously some situations that you need to know about. If you have an object and you read a question that says moving with constant velocity, then it will be represented by a flat horizontal line on a velocity time graph. The reason for this is if an object is moving with constant velocity, that means it's not accelerating. Okay, so it's just moving with constant velocity and it's not changing velocity over time. However, if the object is accelerating and it's got a constant acceleration, then it's represented by a line with a gradient which is the same all the way through. Okay, an increasing line, a positive line, which obviously has a gradient which is the same all the way through. And obviously the opposite is true if an object is decelerating. This can be represented by a line which has a negative gradient, and the gradient will be the same all the way through. Okay, so those are the sort of things that we need to know for a velocity time graph. So let's have a look at this question here. Example 1. So we have a train situation here. The train accelerates for 20 seconds from rest to a velocity of 9 meters per second. It then travels at this velocity for 2 minutes, and the question is find the total displacement in kilometers. So let's just plot a few things on the graph and see if we can complete the graph first before we find displacement. So the train accelerates for 20 seconds from rest to a velocity of 9 meters per second. So from rest means it will start from 0 meters per second, and then it goes up to 9 meters per second 20 seconds later. So that section of the graph we draw by a positive gradient line from 0 meters per second to 9 within 20 seconds. The question then goes on to say it then travels at this velocity for 2 minutes. So it does that for 2 minutes, so this line will go all the way up to 140. Okay, now if it goes all the way up to 140, then the question is find the total displacement in kilometers. Now if you remember from the previous page, and it's given here in the question, displacement equals area under the graph. So what I need to do is find the area of this underneath this graph, and obviously I can split this into two fairly easy shapes, a triangle and this square or rectangle. Okay, so the first section is the triangle area, which will be half times base times height. The base will be 20 times by height of 9, so 20 times 9, so it'll be 90 kilometers. Okay, oops, sorry, 90 meters per second times meters. 90, if it's meters per second, and we've got to be very careful here, meters per second then it's done 90 meters. Okay, and then for the other shape, the rectangle shape, okay, so it's done 20 to 140, so that's 120 seconds times by 9. Okay, now just do a quick calculation there. Which is 1080 meters. Okay, if you add up these two numbers, we get 1170 meters, but remember we want it in kilometers, so we've got to divide by 1000, which is 1.17 kilometers. Does that look appropriate? Well, I think for a train, over a 2-minute period, I think that looks appropriate. Okay, so you just have to be wary of the units that we're looking at. Right, the second example, turn over the page, looks like this. So let's just have a look. So this diagram shows the velocity time graph of a different train travelling from station 1 to station 2. The train moves along a straight railway. Describe the motion of the train, stating the acceleration and velocity in each stage. So, if I look at my graph, there are definitely 3 stages. Okay, so I'm going to call stage 1, stage 2, stage 3. Now for stage 1, we can clearly see that the train is accelerating at a constant rate. Okay, you can clearly see that the gradient is positive, therefore it's accelerating, and obviously it's remaining the same through that process. So it's accelerating at a constant rate. Okay, and if we have to state the acceleration, then acceleration comes from finding the gradient. So we've got to find the gradient of this section of the graph. So change in y over change in x, so it's done 20 meters per second over 10 seconds, so that's 2 meters per second squared. So that's acceleration for that period. Stage 2, we've got a flat line here. Okay, and that would suggest that the train is at a constant velocity, okay, of 20 meters per second. The acceleration is equal to 0. Okay, so stage 1, the train is accelerating at a constant rate from 0 meters per second to 20 meters per second at 2 meters per second squared. Stage 2, the train is at a constant velocity of 20 meters per second, acceleration is 0. Now stage 3, the train is decelerating, okay, and the value of this deceleration, okay, which obviously is a negative gradient, so our value will be a negative acceleration. So we've got to look carefully. It's going from 20 to 0, so the change in y is minus 20 over a 20-second period, so minus 1 meters per second squared. We can have a minus acceleration as acceleration is a vector. Okay. Now, part B. What is the displacement of station 2 from station 1? So they're looking for overall displacement. Now the overall displacement comes from finding the area of these sections. Okay, so the first section, we've got a triangle with a base 10 and a height of 20. Second section, we've got a rectangle, base 50 and height of 20. And the last section, got a base 20, height 20. Now if we find all these individual areas, yeah, so we're going to get displacement will be 10 times 20, which is 200 over 2. This is a triangle, so it's going to be 100, plus 50 times 20 for the rectangle, which is 1000, plus 20 times 20 over 2, which is 200 here. And when you add it all up, you get 1,300 meters, or 1.3 kilometers. Okay, but obviously standard units will be 1,200 meters. That sounds appropriate between two stations. Right, part C. Find the train's average speed during this 80-second period. Right, the average speed, we've got to be very careful here. When we talk about displacement, we're talking about how far an object is travelling from a starting position. So the starting position from station 1 all the way to station 2. And the average speed is obviously the total distance travelled over the total time taken. Okay, so as mentioned before, the speed will be total distance over time. So total distance will be 1,300 kilometers, sorry, 1.3 kilometers, which is 1,300 meters. The train does actually travel that distance, okay, as well as it being displaced from station 1 to station 2, and it does that over an 80-second period, which gives it an overall speed of 16.25 meters per second. Okay, so dotted time graphs as a topic, that's done in the workbook. There are some questions here that you may wish to have a go at on page 135.